Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the intellectual ferment of the early 1960s, particle physics presented a landscape of bewildering complexity. The advent of powerful accelerators had unleashed a veritable menagerie of new particles, the hadrons, whose proliferation defied simple explanation. This particle zoo challenged the very notion of elementarity. Amidst this chaos, a powerful organizing principle emerged from the abstract realm of group theory, the special unitary group of degree 3, or SU3, proposed independently by Murray Gell-Mann and Yuval Neeman. This symmetry, known as the Eightfold Way, brilliantly sorted the hadronic clutter into elegant geometric patterns, or multiplets, baryons. The heavy relatives of the proton and neutron fit neatly into octets and decuplets, as did the lighter mesons. The success of SU3 was undeniable, culminating in the triumphant prediction and subsequent discovery of the omega- particle in 1964. Yet, a profound question lingered beneath the surface of this mathematical triumph. The SU3 symmetry group possessed a fundamental representation, a simple triplet of objects from which all the more complex multiplets could be constructed. The observed hadrons, however, fit into octets and decuplets, representations of higher dimension. The fundamental triplet was conspicuously absent from nature. The consensus among the physics establishment was that these fundamental triplets were a mathematical convenience, a useful fiction for generating the correct symmetries, but devoid of any physical reality. The focus was on the abstract symmetry, the Platonic form, rather than its potential constituents. It was into this climate of sophisticated mathematical abstraction and physical caution that a young postdoctoral fellow at CERN, George Zweig, introduced a paper of stunning conceptual simplicity and radical implication. His 1964 preprint, titled An SU3 Model for Strong Interaction, Symmetry and Its Possible Implications for the Existence of New Hadrons, dared to take the mathematics literally. It proposed that the fundamental triplets of SU3 were real, physical entities. So doing, laid a conceptual foundation for how modern understanding of Zweig's intellectual journey to this point was shaped by the very environment that would initially spurn his idea. A product of Richard Feynman's intellectually vibrant Caltech, Zweig was steeped in a tradition that valued physical intuition and concrete models over purely formal abstraction. Upon arriving at CERN in 1963, he confronted the European-style emphasis on formal symmetry principles. The puzzle of the SU3 classification scheme consumed him. He sought a physical reason for its success, an underlying mechanism that would explain why hadrons obeyed this particular symmetry. His solution was to postulate the existence of a new trio of fundamental particles, which he whimsically named aces, a term drawn from the four-ace hand in bridge, imagining a fourth might be needed for the weak interaction. The core assertion of his paper was elegantly straightforward. Every known baryon was a composite of three aces, and every meson was a composite of one ace and one anti-ace. This simple combinatorial rule immediately reproduced the known octets and decuplets of the Eightfold Way, providing a tangible, physical basis for the abstract group theory. The protons and neutrons were no longer fundamental, they were three ace-bound states. The pions exchanged between them were themselves composite asynthiase pairs. The entire edifice of nuclear and particle physics was to be rebuilt from these more elementary constituents. The true heresy of Zweig's proposal lay in the properties he was forced to assign to his aces. To construct the known hadrons with their integer electric charges, the aces themselves had to possess fractional charges. Specifically, Zweig's model required two aces with a charge of positive 2/3 of the elementary charge, and one with a charge of negative 1/3. This was a conceptual leap of breathtaking audacity. For over half a century, since Robert Millikan's whale drop experiment, the quantization of electric charge in integer multiples of the electron's charge had been a sacred tenet of physics. The postulation of fractionally charged particles seemed to many a desperate and unphysical contrivance. It flew in the face of all experimental evidence and theoretical prejudice. Yet for Zweig, it was a logical necessity dictated by his physical model. The fractional charges were a consequence of taking the SU3 triplet seriously. As a physical object, his paper was a testament to the power of following a clear physical idea to its ultimate niscase, startling. Furthermore, Zweig's work went beyond mere static classification. He explored the dynamical consequences of his model, leading to a profound insight that became known as Zweig's rule, later named the OZI rule by others. He represented particle interactions with simple line diagrams, where lines corresponding to aces were continuous from the initial to the final state. He noticed that certain decay processes, which were allowed by all known conservation laws, were experimentally suppressed by orders of magnitude. His ace model provided a natural explanation. For example, the phi meson, with a mass of about 1020 mega-electron-volts per c squared, was known to decay predominantly into a pair of K-mesons. Its decay into 3 pions, a channel with much more available phase space, was exceedingly rare. In Zweig's model, the phi meson was composed of a strange ace and an antistrange ace. The K-mesons also contained strange aces. A decay into 2 K-mesons could proceed by simply creating a new asynthetase pair from the vacuum and rearranging them. The ace lines flowed continuously. A decay into 3 pions, which contain no strange aces, would require the initial strange-antistrange pair to annihilate each other, a process represented by a disconnected diagram. Zweig posited that such hairpin diagrams were suppressed. This was a powerful, predictive rule derived directly from the physical picture of constituent aces. It transformed the model from a simple bookkeeping device into a tool for understanding the dynamics of strong interactions, a clear signal that the aces were behaving like real, interacting particles. The reception of Zweig's paper forms a sobering chapter in the history of science. While Gell-Mann was simultaneously and independently developing a similar idea, which he called quarks in a playful nod to James Joyce's Finnegans Wake, his presentation was vastly different. Gell-Mann's 1964 paper, published in the prestigious journal Physics Letters, framed quarks as primarily mathematical entities, hitching on their physical reality and suggesting they might be a useful abstraction from which the currents of a strong interaction could be built. This cautious framing made the idea more palatable to a skeptical community. Zweig, by contrast, was an unabashed realist. His Sonderprint spoke of aces as real particles, waiting to be discovered. This forthrightness, combined with the radical nature of fractional charges, elicited a response from the Sohn establishment that ranged from deep skepticism to outright hostility. The leadership at the laboratory strongly discouraged him from submitting the paper for publication in a journal, viewing the idea as crackpot science that could tarnish CERN reputation. Consequently, Zweig's foundational work circulated only as a care of internal CERN reports, its audience limited and its impact initially muted. It became a piece of underground literature, a whisper of a revolution that the official organs of physics refused to broadcast. The reluctance to embrace the ace or quark model was rooted in 2 profound scientific difficulties. The first and most obvious was the persistent failure of experimentalists to find any evidence for fractionally charged particles. Despite numerous and diligent searches in cosmic rays, in stable matter, and in the debris of high-energy collisions, these fundamental constituents remained stubbornly elusive. If they were the building blocks of protons and neutrons, why could one seemingly never break a proton apart to liberate them? This problem of confinement was a deep mystery that cast a long shadow over the entire enterprise. The second issue was more subtle, a conflict with the fundamental principles of quantum statistics. A particle like the delta plus resonance, a key member of the baryon decuplet, was understood in the model to be composed of 3 identical aces of the same type, 3-up aces, in modern parlance, all with their intrinsic spins aligned in the same direction to produce the particle's total spin of 3 halves. According to the Pauli exclusion principle, a cornerstone of quantum mechanics, 3 identical fermions were forbidden from occupying the same quantum state. The ace model, in its simple form, appeared to violate this bedrock principle. These twin problems, the observational absence and the statistical paradox, provided ample justification for the community's caution and ensured that the quark model would remain on the fringes of theoretical physics for several years. Vindication, when it came, arrived from an unexpected quarter. It emerged from the thunderous electron beams of the Stanford Linear Accelerator Center SLAC in the late 1960s. In a series of landmark experiments, a team led by Jerome Friedman, Henry Kendall, and Richard Taylor fired high-energy electrons at proton and neutron targets. In a process analogous to Ernest Rutherford's discovery of the atomic nucleus, they observed that the electrons were scattering at large angles far more frequently than would be expected if the proton's charge were smoothly distributed. The data powerfully suggested that the electrons were striking hard, point-like scattering centers within the proton. Richard Feynman, analyzing these results, dubbed these constituents partons, a deliberately neutral term to avoid commitment to any specific model. It soon became clear, however, that the measured properties of these partons matched precisely those predicted for Zweig's aces and Gell-Mann's quarks. They were spin 1/2 particles, and their inferred electric charges were consistent with the values of positive 2/3 and negative 1/3. The SLAC experiments provided the first direct, compelling experimental evidence for a granular substructure inside the nucleon. Zweig's physical intuition, his insistence on the reality of the constituents, had been stunningly confirmed. The aces were real. The theoretical difficulties also began to yield to a new, deeper understanding of the strong force. The spin statistics problem was resolved through the introduction of a new, hidden quantum number, first proposed by Oskar Greenberg in 1964 and later developed by Mu-Young Han and Yukihiro Nambu. This new property was whimsically named color. In this extended model, each type of ace or quark came in 3 distinct colors, say red, green, and blue. The Pauli principle could now be satisfied because the 3 aces in a particle like the delta++, while identical in flavor and spin, could be distinguished by their color. The theory mandated that all observable hadrons must be colorless or white, meaning they must be combinations of colors that are neutral with respect to this new charge, such as the red-green-blue combination for baryons or a color-anticolor pair of mesons. This seemingly ad hoc addition turned out to be the key to a complete dynamical theory. The color charge was identified as the source of the strong force itself, mediated by the exchange of 8 massless vector bosons called gluons. This theory, known as quantum cryodynamics or QCD, was finalized in the early 1970s. QCD provided a fundamental explanation for both the successes and the puzzles of the original quark model. It explained confinement, the inability to observe free quarks, as a feature of the strong force, which, unlike electromagnetism, becomes stronger at larger distances. Pulling 2 quarks apart requires so much energy that it becomes more favorable to create a new quark-antiquark pair from the vacuum, resulting in the production of new hadrons rather than free quarks. The theory also explained the suppression of decays described by Zweig's rule as a consequence of gluon dynamics. In retrospect, George Zweig's 1964 paper stands as a monument to the power of physical insight and intellectual courage. In a field dominated by false symmetry and abstract mathematical structures, he insisted on a concrete, mechanical picture of reality. His unique and indispensable contribution was this very insistence on the physical existence of his aces, in stark contrast to the more ambivalent initial stance of the wider community. While the quark model was a product of parallel evolution, Zweig's formulation was arguably the one that most clearly and bravely articulated the physical revolution it entailed. The story of its suppression and eventual vindication is a classic, if somewhat cautionary, tale of scientific progress. It demonstrates that profound truths can be overlooked when they clash with established dogma, and that sometimes the most straightforward, even seemingly naive, physical picture can capture a deeper reality than more sophisticated but less committed abstractions. Zweig's aces, born in a CERN preprint that was denied a wider audience, ultimately broke free of their confinement, not in an experiment, but in the collective mind of the physics community. They provided the unshakable foundation upon which the standard model of particle physics was built, transforming a bewildering zoo of particles into a well-ordered system and forever changing our perception of the fundamental architecture of the universe.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.